Hello, everyone. I'm Xiyang, a PhD student from Carnegie Mellon University. This work is about uncovering the source of machine bias. It's a joint work with Yan, Beibei, and Tian. This is an early stage work, so any comments are highly appreciated. For machine bias, a very natural question to ask is where does the bias come from? To answer this question, let's look into the data generation and model building pipeline. The whole pipeline includes multiple steps. First is data generation, and then the population selection, human measurement and labeling, data pre-processing, model building, and the final deployment. Every step in this pipeline could introduce different types of bugs. Almost all this work focus on steps after we get the data set. Here we take one step back to where we introduce human design bugs. It was found that human bias is a crucial source of errors and bias, and sometimes even a small bias from humans can be amplified by AI or machine learning. In this work, we answer the following questions. First, can we quantify human design bias more granularly? Second, how does human bias affect the market outcome? Last, to what extent a machine learning algorithm trained on historical data inherit human bias? We follow the taxonomy of human design bias by Bohan 2019. They documented two underlying sources. The first type of bias is preference-based bias. Preference-based bias arises when evaluators have animus towards a particular group, and it persists and doesn't change a long time. Another one is belief-based bias. It arises when evaluators' subjective belief about a group leads them to less favorably treat individuals from this group, especially compared with people from the regular group with the same observed performance. Belief-based bias can get updated when we observe more and more signals from the group. This might be a little bit abstract to understand, so let me give you some example. Let's say I'm a big fan of Google Pixel, and I know a lot about Google Pixel, but not much about iPhone. At this time, I prefer Google Pixel to iPhone. And my friends with iPhone, they keep telling me how good it is. And recently they showed me again, look, iPhone is pretty powerful. With iPhone now I can use a Magic AirTag. So I keep receiving positive signals about how good iPhone is. If I update my belief of the iPhone after getting these signals and make a more informed comparison between iPhone and Google Pixel, I realize that I like iPhone more than Google Pixel. Then it means I have a belief-based bias on iPhone initially. But if I keep preferring Google Pixel, no matter how many signals I have received, then it is preference-based bias. In a static setting, preference and belief-based bias mix up with each other, and it is hard to isolate them when observing human decisions. However, in a dynamic setting, we are able to distinguish the two biases. This is because across periods, preference-based bias can persist, while belief-based bias can be mitigated when we get new signals. The disentanglement of the two types of bias is important. First, the static exception of bias may overshadow the potentials and the value of learning behaviors in decision making. Second, with disentanglement, we are able to dynamically trace the evolution of bias along long-time decisions. And it also enables us to unravel the influence of different types of human bias on decision outcomes. Moreover, the two types of bias lead different ways to deal with. And last, when we feed human-generated data into algorithms, machine learning could behave differently when inheriting two different biases. Our research context is a micro-long platform, and we focus on the long application and evaluation process. When a new user joins the platform and apply for a loan for the first time, she needs to provide her personal information and demographics. The platform uses human evaluators to make the loan granting decision. Based on the demographics, the human evaluator would form a belief about the credit quality of this new applicant and then compute a utility of approving this loan. Based on the utility, the evaluator makes a decision to approve or reject this loan application. If a user was approved a loan before, then she is a repeated applicant. In addition to the demographics, the human evaluator observes her previous loan repayment behaviors and updates the belief of the credit quality based on the repayment behavior. And then the evaluator forms the utility again and makes the loan approval decision again. And for repeated users, such a decision process happens again and again when she applies repeatedly. This unique context fits our research questions pretty well. First, it has a simple and clean evaluation process, and we have granular data of users and each loan's economic outcome. And this setting is a typical human AI decision-making setting. This company use human evaluators now, but plan to deploy AI in recent future. Also, literature shows microfinance error is common to CBAs. Another important point is that this is a dynamic learning process and we have plenty of repeated users so that we can distinguish the two types of BAOs. For our counterfactual analysis, we have a certain data set. It covers all the loan records from 1 month experimental period. During this period, all applicants are approved. This gives us true labels of all users. This would guarantee our results are based on all user distribution rather than just the approved users, which have a different distribution with the whole user pool. For the data, we have more than 300,000 loan application records spanning from February 2015 to December 2017. It's from about 140,000 borrowers. We have individual attributes such as gender, income, housing, residential province DPI. We also have loan-level attributes such as application time, loan terms, interest rates, and loan repayment behaviors. For the loan repayment behavior, the evaluators observes one is final overdue days of the loan, and second is overdue days of each installments. Third, we observe whether the borrower actively repays the loan. And last, we observe whether the borrower gets financial help from family and friends. This figure shows approval rate by the number of applications of each gender. For the new applicant, the approval gap between two genders is relatively large. It's about over 10%. For repeated users of their second to fifth application, the gap decreases to about 6%. With a few more repeated applications, the gap becomes only about 4%. And for repeated users with more than 10 applications, it's about just 2%. This shrinking trend suggests that the learning helps amend the evaluator's prior bias toward gender, but even after 10 repeated applications, there are still a small gap left, which means there could be preference-based bias. In reality, only hundreds of people have more than 10 repeated loans, which means most users are rejected even before their signals can be learned by the evaluator. We model the credit evaluation process as a discrete choice, where for each loan application by applicant I at time t, the evaluator decides whether or not to approve the loan application. The belief-based bias is incorporated in our models through the prior belief, and the preference-based bias is incorporated in our models through a term in the utility function. Please refer to our paper draft for the model details if you are interested. We estimate the model parameters through MLE, and for the preference-based bias, the estimate is significantly elective. This implies there is a significant bias for gender, which cannot be corrected by observing repayment behaviors. The estimation of the belief-based bias is significantly positive, suggesting that there is a prior belief in better families' credit quality. Both the preference-based bias and the belief-based bias have expected signs, implying that the evaluator has a preference for female applicants. With our model, we conduct two sets of counterfactual policy simulations to figure out the effects of eliminating these biases. First, we investigate how does eliminating preference-based bias affect the company's welfare and the borrower's welfare. Second, we examine how does removing gender from the prior information affect the company's welfare and the borrower's welfare. All these counterfactual analyses are based on the second data set we have. It covers all the loan records of 1 month experimental period, during which all applicants are approved so that we have true labels of all users. On the company side, we compare the expected profits of the current design process and the counterfactual ones. We observe that when we remove the belief-based bias, it leads to a higher expected profit with an increase of about 14%. And by eliminating the preference specifiers, the platform obtains better profits too, but the increase is smaller, just about 2%. And when we're removing both spouses, we get the maximum increase of about 16%. The interesting point is that the original intention of the evaluator is to make use of the gender information to better identify users' credit quality and therefore earn more profits. But in reality, it leads to sub-optimizing and lower profits because of the biases. On the user side, we examine the change of the gender gap in the credit evaluation accuracy, which is females' accuracy minus males' accuracy. When the belief-based bias is removed, the gender gap for the credit evaluation accuracy becomes smaller. It decreases about 19%. And when we remove the preference-based bias, the gender gap also becomes smaller. It's about 1.24%. The good thing is that belief-based bias is much easier to eliminate, and the removal of belief-based bias can give us 15 times more decrease than the removal of the preference-based bias. Also, when both biases are rolled out, we achieve the smallest gender gap for the credit evaluation accuracy. In conclusion, we have proposed a way of using structural models to distinguish and estimate two types of human decision biases, that is belief-based bias and preference-based bias. The estimation results imply that the evaluators hold a preference-based bias in favor of female applicants. They also hold a belief-based bias with a larger prior belief in females' credit qualities. By observing the repayment behaviors, the evaluators can quickly update their belief of the borrower's credits. And through policy simulations, we found that the elimination of either the preference-based bias and the belief-based bias can increase both the company's welfare and the borrower's welfare. Currently, we are also trying to fit the real-world data set and the counterfactual data set into machine learning algorithms to examine how human bias encoded in the training data is inherited by machine learning algorithms. This will be the most interesting part of this paper. Keep an eye on our work if you are interested. Thank you for your listening. Feel free to reach out if you have any thoughts.